Hello, we are starting topic 8, controllers. There's a subtopic for this, and that's finite state machines. And I explain why we start with the topic of controllers, and then we go into finite state machines. The topics that we'll be covering: finite state machines, then we talk about the state diagrams, then we talk about the various types of state diagrams, the state machines, and talk more about the modeling of sequential components in Hoffman fashion. And then we talk about implementations. And finally, at the very end, we will do a very simple example, a complete example, not only a controller example, but one that has a data path and controller. See, a complete digital system has a data path and a controller. Okay? Now, the data path for a digital system is the one that has the ALU, has the adder, has the subtractor, has the registers, has the counters, shift registers, and all that. And that's where the what's are done. Okay, what's are done means that I'm adding. So this is what I'm doing. I'm adding, I'm storing, I'm counting, I'm shifting, and so on. And then there is a whens. When are these operations being done? Okay, and the whens are controlled by the controller of the system. So far, what we have shown you has been the various components of the data path, like the comparator, like the adder, and so on, like the multiplexer. And we have shown how we can connect them together. Okay, and which is basically wires, or sometimes with multiplexers. But then there is someone sitting there on the right-hand side here that is called the controller. That controller is an important component and issues control signals to the data path. The controller receives inputs from the data path via status signals. The controller also receives signals from the outside world telling it get started or put the data on such and such output bus and so on. But the controller itself is the one that makes the decisions, but it orders the data path to do this. Okay, so the decision making is done in the controller. And the signals that control things only go to the controller. Even the data path, when it wants to make a decision, it doesn't make the decision itself. It sends this information, the status information to the controller. The controller decides, okay, now this is supposed to be done. So what it is, controller is a sequential component. Why? Because it has memory. Because it has to have memory. Because it is making decisions. Okay? If I want to talk about a controller, I have to talk about a controller a real controller, has signals coming from everywhere and making a lot of decisions and all of that. Okay? Which may be not possible at this stage in learning digital systems. So instead, what we do is we go into a smaller controller. Controllers are state machines, finite state machines. These are states, finite number of states, 10 states, and they go from one state to the next one based on the conditions. Okay, based on the conditions, they go from one state next to the next one. In each state, they make certain decisions. They issue signals to the data path or to the outside world, and the outside world makes takes the decisions and does what it's supposed to be. The data path also makes this, takes the decisions, and then it clocks the data into its register, or it tells its ALU to do adding instead of subtracting and things like this. Okay, so a controller is a state machine, is a finite state machine. Finite means that there are a fixed number of states. Okay. So a controller is a complex finite state machine. My problem is, what do I do? Do I come in and show you a complex finite state machine for a, let's say, a processor that has 40, 50 instructions and does this and this? I'm not going to be able to do that. So what I do is I bring it down into a very, very simple finite state machine. And that finite state machine is usually one that has one or two inputs and one or two outputs. We use that finite state machine to show you the overall properties of most controllers. So we take a simple finite state machine, not with too many inputs, not with too many outputs, with one input, with one output, and we exercise that. We show you the Verilog description of it. We show you the hardware implementation of it. See, because if I have 4 or 5 states, one input, one output, I can easily turn that finite state machines to what we already know, which is flip-flops, Carnot maps, Boolean expressions, flip-flops, this and that, and show you the actual hardware right in front of you. But if I take a real controller, I won't be able to do this. So if you look at the controllers that we are showing, don't be surprised that they're so easy. On the other hand, the controllers that you will be seeing, or the finite state machines that you will be seeing, are general enough that you can very easily expand what you learn here into very complex systems. All right, so let's start with what we have already seen. I start with terminology. Okay, what we have already seen is at the end of the flip-flops, we talked about a modulo 5 counter, a counter that goes from 000 to 001, 0101 to 010, and so on. And that was a counter that we took the transition table, then we said let's do the D flip-flop, and we turned it into Q to Q1, Q plus Q0, defined those, or actually defined D1, D2, D1, D0 in terms of the existing input, existing state of the machine, and therefore we came up with truth table for this, and then from this we came up with the Carnot maps and so on. Okay, and we were able to develop a circuit like this. Okay, I'm giving this a different flavor now. See, this is my table. I go from this state to this state, from 001 to this state, from 010 to this state. Okay? Instead of showing this in a tabular form, I like to show this to you in this graphical form on the right-hand side, which is basically the same thing, right? You are saying I'm going from 000 to 001 state, 001 to 010 state. When you go to 100, you go to 00 state. Well, definitely what I'm showing here on the right hand side is more attractive than what I'm showing on the left-hand side. Okay? You can read this a lot better than having to follow tables. And therefore, this becomes something that if I want to describe a complex controller, that complex controller can more easily be described in this form on the right hand side than the form on the left hand side. This form is called a state diagram, which is exactly what it is. It looks like a flowchart of some sort. It's called state diagram. It's a diagram that tells me my states. I'm going from this state to this state. Here, transition from one state to the next is unconditional and only depend on the clock edge. Meaning that if you want to go from 010 to 011, a clock edge takes you there, but you don't need any input conditions. This is a very simple state machine. This state diagram. This state diagram becomes the interface for me to design controllers. And controllers are finite state machines. And therefore, this becomes a state diagram representing the first step in the design of these controllers. So when, for example, when you're deciding something, you think about, okay, if this happens, then I'm going to do this. If this happens, I'm going to do this, and so on, right? And here we do the same thing. You say, well, if such and such input happens, I go from this state to the next. On the other hand, if this input does not happen, I go to another state. So let's just look at one state diagram, which is a little bit more complex than this, where decisions are being made. All right, this was the state diagram, and then that was the first step in the design process. Then we go into the transition tables. Then you have seen that we go from there to the D table, the input table, and then from there you go into Carnot maps, and eventually you have your design. Okay, eventually you have your design, which is this. Okay, and then this design has a sequential part, a clocking part, and also a combinational part. So what I'm saying is, if my first step is a state diagram, then going from state diagram to transition table to the table for the D flip-flops, then from there to the Carnot maps, then from there to the circuit diagram is an easy thing, is a procedural thing. So let's now focus on state diagram. I'm designing something, let's say, just a different counter than what I showed you there, which is that counter just goes from 000 to 001 and then on to 100 and then back to 000. Okay? Now, the counter I'm doing now is going to be a little bit different. Decisions are being made. It's an up-down counter. It doesn't always count in the increasing order. Sometimes it counts in the decreasing order. Therefore, going from one state to the next requires looking at certain input conditions. This is something you did not have in the previous state diagram. Okay? This is what I want. I want a counter that goes for, if the U or the up input is 1, it's counting in the up direction. That means 000 becomes 001, 001 becomes 010 in the up direction. And but then if up is 0, this is up. If up is 0, it's counting in the down direction. And in that case, if my count is 010, it becomes 001. That means 2 becomes 1, 1 becomes 0, and then it rotates back. Okay? Not a very complex circuit, but it's just one that shows a little bit more of the value of state diagrams. So if this is the design I want to do, this is where I start from. This becomes the interface of my design. Okay? This is a good representation of state machines or state diagrams for designing state machines. In state 000, if U is 1, I go to 001. That means I'm counting up. If U is 0, I'm counting down. That means in 000, I go to, in 000, if I'm counting down, I go to 100. Okay? And then from 100, which is 4, I go to 3, to 2, to 1, to 0 eventually, and then back, if this is down counting. So what I'm really showing here is if you tell me to design an up-down counter, I would start with something like this. I would start with this state diagram. Once I come up with this state diagram, I say, okay, now let's turn this one into the state table. So unlike what I showed you in the at the end of the flip-flops, which is the state table is what we started with, what I'm saying is, yeah, for easy ones, you can do that. For more difficult ones, where more decisions are being made, state table is not what you can start with immediately, or transition table is not what you can start immediately. You better start with state diagram and then eventually from there go to circuit, which will show you the steps. For this though, I'm not going to go through the entire exercise. All I wanted to show you here was that a state diagram is the first step in describing a piece of hardware. You can always go into the Verilog description of it. Okay, and you can actually make this Verilog description if you don't really feel like doing these steps of creating the hardware yourself. Okay, what you can do is just write the Verilog description, follow the proper rules of the Verilog description, and then just give it to the synthesis tool. The synthesis tool does it for you. Okay, I'm going to show you the Verilog description. That doesn't mean that I'm not going to show you the manual way of designing state machines and doing the procedure by hand. Okay. All right, this is a up-down counter, which is this. The state diagram is this, and I'm going to show you the relation between this diagram and then the Verilog description of it. The inputs, the clock and the reset are the inputs. Okay, that we don't really touch. Then you have an up control. This one here. If up control is 1, here, you're going up. 1 becomes 2, 2 becomes 3, 3 becomes 4, 4 becomes back to 0. Rollovers. It rolls over. The output of your counter is a 3-bit count, and you're declaring it as output count. Okay? Okay? You write an always statement to define the transitions exactly according to the transitions of the state diagram. Except that when you're doing this, you think that eventually this circuit becomes a combinational circuit, a combinational part with an input up and the count output, and this makes several flip-flops or puts values in several flip-flops. Okay, remember, let's go back here. See, this is what I have, right? Eventually, when I design by hand, I will come up with several flip-flops, a combinational circuit, and then a feedback from the combinational into flip-flops, and then from flip-flops back into the combinational part, right? And then when I'm describing the Verilog, even though I'm not doing this manually, I will still follow this procedure. And therefore, I have a part that does the clocking for me. For the input of that, I declare this is my present state, this is my next state. Present means what is now the state of my machine, like for example 001. The next state is what happens if under certain conditions, under these input conditions, clock arrives. That becomes my next state. Okay, and therefore the input up and the present state together, they decide on what's going to be my next state. My next state won't become my present state until the next clock arrives. So what I'm showing in blue here is a combinational part that makes a decision based on the present input and the present state, makes a decision for the next state. And that is a combinational part. As you have seen, this is a combinational part. Okay? So, let's describe that blue part. Always, always, when my present state or my up input change, and therefore I have a Verilog description for combinational part representing exactly this blue stuff here. The input of the blue part is the present state, and the output of it is next state, and therefore I'm declaring my present state and next state on line 2. Okay? Those are not necessarily my input and output of the circuit. Let's describe this. We have talked about always the statement describing combinational parts. Let's describe this. Always when the present state or the up input, if they change, flow begins. As soon as the flow begins, next state, which is the output in this case here, on line 5 is set to inactive value, and therefore it's set to 0. Then I say on line 7, if up is 1, then the next state becomes 3 tick D1. Okay? 3 tick D1 means the next state becomes 001. Okay, let's look. When I'm in state 0, if up is 1, I go into 001. So what I'm showing there, I won't be able to show you the line number, line 7. Okay, how far can I go? Yeah, I can do that. What you are seeing on line 7 corresponds exactly. Look down below. Corresponds exactly to the two states I'm showing there. When you are in 0, 0, 0, that means line 7 says case present state is 0. Your next state becomes, if up is 1, your next state becomes 1, which I'm showing in blue here in the state. Otherwise, you go to state 4. If up is 1 and if up is 1, you go to state 1. If up is 0, which is this arrow on the top, that takes you to state 4. So for every state that you see here, there is a line in the case statement. Okay, I'm gonna show you this. Let me do the next one. For this state, state 1. If u is 0, which is line 8. If u is 0, which is up, okay, the up input, then the next state becomes 0. Look, if u is 0, the next state goes from 0, 0, 1 to 0, 0, 0. If u is 1, means you're counting up. This becomes 0, 1, 0, and therefore you are seeing that if up is 1, your next state becomes 2. And then the same thing for the rest of them. So you're defining your transitions in terms of the present input and the input. You only have one input here, which is the up count. And then you follow through, and then you also put this line 12 there, which is default. If something goes wrong and you never have any of these states, then the next state is always the reset state, which is the 0, 0, 0. So what I've done so far is I've described that combinational part right up there for this state diagram, and but then this is not the end of it. Okay, I still have things to do. This state diagram translates to a combinational part in blue and a sequential part, which I'm going to show you in dark green. What does that do? On the clock, next state clocks into the present state. We have already seen flip-flop Verilog description, and that's where you consider the resetting, the setting, the control of the flip-flops. Here I only have an asynchronous reset, and therefore I describe this in terms of asynchronous reset. If reset is active high, then my present state, which is the output of the flip-flop, becomes 0, 0, 0. Otherwise, the input, which is the next state, look at the input. The input is next state, gets clocked into the present state. I'm also showing in this diagram some outputs. In this particular description, the outputs are just the count outputs. Okay, I'm separating the outputs from the states of my machine, but then I say, well, my count output is really nothing but my present state. Now, in some other more complex ones, the present state may be mixed with some of the inputs, and there would be a logic part on the inputs and so on to form the outputs, and not directly present state connecting to the counter. Nevertheless, I describe this so that it follows the general description of state machines. Okay, and always a statement for transitions, and always a statement for clocking, and always a statement or an assign statement for assigning the outputs. All right, what we have covered is the concept of finite state machines and describing finite state machines, and skipping the procedure and going from one state diagram directly to Verilog and letting the synthesis taking care of it. Let's go into more state machines, more state diagrams, and let's learn manually how to design.